Hello everyone. Okay, so we're going to take a look at Math Reasoning Lesson 2, which is going to focus on deductive reasoning. So when we talked about inductive reasoning in the last lesson, we said that inductive reasoning is a type of reasoning which we arrive at a conjecture based on experience, observations, or patterns. So we're looking at just set examples of things that are going on, and then we're going to say, oh, well, we're going to assume that it continues. Inductive reasoning does not guarantee that a conjecture or an educated guess is always going to be true, as we found in some of the cases last time. Inductive reasoning can never be used to prove a conjecture. Just because I have however many case examples, I'm never going to be able to use it to prove that it's going to be true every single time. So, inductive reasoning can play a part in discovery of mathematical truths, but some other form of reasoning is required to find something that will always be true. So, if I'm using logic to reason, well, in this case it says Susie dropped off a film at quick 1 hour photo. Quick 1 hour photo advertises that your film will be developed within 1 hour or there is no charge. Susie dropped off the film at 10 o'clock a.m. It wasn't developed until 11:50 a.m. What can Susie deduce from this? Susie's film will be free of charge. They had 1 hour to develop it, they took an hour and 15 minutes to do it. It just makes sense given the situation. When we're using deductive reasoning, which is a form of logical reasoning, then we can use true statements or facts to arrive at a conclusion. In the scenario above, Susie used deductive reasoning to conclude her film would be developed free of charge because there was the fact of they don't charge if it takes longer than an hour, and the fact of it took longer than an hour. If I'm writing a conclusion which can be deduced from each pair of statements, well, if it says every whole number is an integer, and 6 is also a whole number, then that means that if 6 is a whole number, every whole number is an integer, 6 is an integer. If water freezes below 0 degrees Celsius and the temperature is currently negative 15 degrees Celsius, then water will freeze. We're talking about a theorem. Unlike a conjecture, a theorem is a statement which can be proved using logical or deductive reasoning, which means a theorem is something that is absolute. It's not just an educated guess, it is something that will work all the time. Alright, so if we're taking a look at example 2, in lesson 1 we used inductive reasoning to write a conjecture that the sum of three consecutive integers was divisible by 3. So if I had x plus 1 plus whatever it happened to be. When we use deductive reasoning to prove that this is true, then this is where we're actually going to use variables to show, well, every single time this is going to work. If I said that the first number is x, if I said that the second number is x plus 1, and if I said that x plus 2 was the third, then that means that if I have x plus 1 plus x plus 2, then that is going to combine to be 3x plus 3. Because I can factor 3x plus 3 into 3 and x plus 1, I know that this is going to be a multiple of 3 because a multiple of 3 means that I can divide it by 3, and we just showed that 3 is one of the factors. So no matter what the numbers are, it's always true. For the second case, it says complete the chart and make a conjecture using inductive reasoning. So we're going to pick a number. Let's say the number will be 1. If I add 7 to that, then my number is going to be 8. If I multiply that number by 2, then it's going to become 16. If I subtract the original number, then I'm going to get 15. Subtract 2 from that, and I get 13, and then subtract the original number, and I wind up with 12. Let's pick another number. Okay, then let's pick 3. If I take 3, I add 7, I'm going to get 10. I multiply by 2, I get 20. Subtract the original number, and it's going to become 17. Subtract 2, and it becomes 15. And subtract the original number, and I'm going to wind up with 12. Okay, well, I got the same answer as I got in case 1. Let's pick another number. Let's say the number is going to be 8. So I'm going to take 8, and then I'm going to add 7 to get 15. I'm going to multiply by 2 to get 30. I'm going to subtract 8 and get 22. Subtract 2, and I get 20. And subtract 8, and I'm going to get 12. Well, what's my conjecture for everything that I can see here using inductive reasoning? If I follow this process, the final answer will always be 12. Now, that was using inductive reasoning. I took some case examples and showed it. If I'm using deductive reasoning, I'm going to use variables, in this case the letter x, for my number, to prove that no matter what number I pick, it's always going to be true. So, I'm going to start by saying that x is my original number. If I add 7 to x, well, we already know that's going to be x plus 7. If I multiply what x plus 7 is by 2, then I'm going to say that it would be 2x plus 7s, which would also be the same as 2x plus 14. I got to double the x and double the 7. Subtract the original number, so I'm taking away an x, and I'm just left with x plus 14. Subtract 2, so I can take that away from the 14, and I'm going to get x plus 12. And then I subtract the original number, the x's are gone, and I'm just left with 12. So we've proved that whatever the original number is, the final answer will always be 12. Does the original number have to be less than 10? No. X can represent any number. X isn't specifically a number less than 10 or between 1 and 10. X can be literally anything. And as we've seen, even if we start with x, which can be any number, the final answer always winds up being 12. Okay. So, in this lesson, we'll be considering statements involving odd and even numbers. Here is the notation that we use. We'll say 2n, where n can be any natural number, is always going to represent every possible even number. We can say 2n minus 1, where n is an element of the natural numbers, for odd numbers. If we wanted to, we could also say 2n plus 1, because that would also be true. So, why is it that 2n can be used to denote every even number? Well, 2n has a factor of 2 and n, which means that 2n represents any multiple of 2. because if I take any n and I multiply it by 2, then any multiple of 2 is also an even number. If it's a multiple of 2, it's divisible by 2. Even numbers are just divisible by 2. Why is it that this one works? Well, because if 2n is going to be every even number, then every odd number is 1 away from an even number. If the odd numbers are 2, 4, 6, and 8, then the even numbers are going to be 1, 3, 5, 7, going on and on. It's always going to be 1 away from each other. All right. So when it says, when two odd numbers are added, their sums are always even. First, we're going to use inductive reasoning. We're going to pick 3 cases and see if it works. So I'm going to pick 2 odd numbers. Well, if I have 1 plus 5, then that's going to be 6, which is even. If I have 3 plus 11, that's going to make 14. That is also even. And if I pick 5 plus 7, that's going to give me 12, and that is also even. So far it's working. If I'm using deductive reason to complete the proof, then let the numbers be 2n minus 1 and 2m minus 1. The reason why is because I'm going to say that the n is going to be one of the numbers, m is going to be a different number. So I'm going to say that if I have 2n minus 1 plus 2m minus 1, then that's going to give me 2n plus 2m minus 2. And I can factor all 3 terms by 2. So I'm going to factor out a 2 and get n plus m minus 1, because 2 has a factor that comes out. This is a multiple of 2. It must be even. Okay. So, I want you to go and try some of the practice. And remember, when we're replacing these, we always start, like we see in here, with just picking some numbers for inductive reasoning. If I want to prove it using deductive reasoning, make sure that you're substituting in that variable. The variable will show that it will work for all sorts of different cases, literally pretty much infinite cases, not just the specific cases you picked. Okay, let me know if you have any questions.